It is also helpful to categorize elements in the periodic table, groups of elements, according to what phase they're in at room temperature. So let's look at this. Okay. This periodic table shows what's a gas, a solid, and a liquid at room temperature. Let's start with gases. Over here on the far right side, the up and down column on the far right side, those are all grouped together and they're called noble gases. Well, I tried to label them. You're fairly familiar with these. They come across in our daily lives often enough. Probably the most common one is helium. We go to a child's birthday party, we find balloons floating around because they're filled with helium. Now the interesting thing about helium is that that balloon sometime during the party might pop, and we've got this pure chemical helium floating around in the room, and if a lot of them popped, that could be a lot of helium. And there's lots of birthday candles going on, and so if it's flammable, it could catch it on fire. Why would we do that to our children? And the answer is that noble gases all have this property that they're very inert. They do not react with anything. They don't even form compounds with anything. So when this balloon's hanging around and it pops, it will do no harm to anybody. Even it's to such an extent that even after the party's over, some adult will frequently this way. Poke a hole in the balloon
and breathe in the gas and have their voice change for fun. But you might ask the question, why would you subject your very sensitive lung tissue to this pure chemical? And the answer is that helium is so inert that it won't even hurt your lung tissue. Now the same will be true for that group, noble gases, which include neon, argon, krypton, xenon, and we find these things in many situations where they're needed to be inert. Neon we find in high temperature lighting. Argon is sometimes put into light bulbs. So when the filament heats up to 10,000 degrees, it can't react with anything because it's surrounded by this unreactive argon. Now still in gases, we can go to another group. They're called the halogens. Now the halogens are the column right next to the noble gases. I've got a little thing to put on there. Okay. And not all halogens are gases. We'll look at two that are, but they are all similar in that they're very highly reactive in distinction to the noble gases. Fluorine and chlorine are the two light blue shaded ones that are gases. They have a long and interesting history. If we look at chlorine, that one's probably more commonly seen in our daily lives. On the negative side of things, historically chlorine was isolated in large pure amounts and used as the first chemical warfare agent. Very effective at causing people's eyes and lungs to completely malfunction and hurting many soldiers and killing many in wartime. It's such an awful way to conduct war that in fact there are treaties around the world against using chemical weapons because of chlorine. Now on the positive side, we see chlorine used these days as a disinfectant. It's put into our water supplies. Sometimes you can even taste it, but the chlorine amount is so small that it won't hurt you, but it will save you. It will still be able to kill microorganisms that might give you disease and make you sick. Chlorine is fairly familiar to us in the sense that we can go to swimming pools and compounds in the swimming pool, as they decompose, let chlorine gas come out, and we can feel the stinging action of a slight amount of chlorine gas on our eyes, or maybe even if on our skin as well. Fluorine, if we go there, the F, is more reactive than chlorine, and in our daily lives we generally don't run into it so much. However, fluorine and chlorine are interesting in that they make very stable compounds and very useful compounds. For example, if you go to the store and get some sort of a plastic pipe, it is frequently polyvinyl chloride. So the plastic has been reacted with chlorine, and it makes a very stable, very inert pipe. Fluorine is even better. You can buy Teflon tape or Teflon coated cookware that is completely inert and very stable, and it's because a plastic coating has been reacted with fluorine. We also see them in compounds like for fluorine, sodium fluoride put into our drinking water to make our teeth stronger, and for chlorine, sodium chloride, which is such a stable compound in distinction to pure chlorine by itself. Sodium chloride is such a stable compound that we eat it as table salt. Moving along to the left, we go from the noble gases to the halogens, and then we've got this combination, nitrogen and oxygen. They are gases in our atmosphere. Very interesting. Nitrogen is literally 78% of our atmosphere. It's the main gas in any air that we run into. Oxygen is number 2. Oxygen is 21%. So if I take just the air between my hands and I were to separate it out into its component gases, from here over to here would be all nitrogen. Then from here to about here would be all oxygen. And if you're paying attention to the numbers, you would realize there's only 1% of this air left over, and in that 1% of air, that's where all the other possible gases are. So nitrogen and oxygen are the main thing. Are they reactive? Are they important in our lives? Of course. We are sitting here breathing because we need the oxygen to get into our bodies and to react with compounds in our body to give us energy. We also find oxygen reacting with almost everything. Not really often, very quickly, sometimes it is, but it will react to some degree with almost everything in our environment. Metals. Where'd my metal go? I have my nice rusty metal. When you see corrosion and rust on metals frequently, it's because they are reacting with oxygen in the air. You may want to be careful of this as well. If you get a finely divided metal, sort of like steel wool, or maybe some sort of aluminum or magnesium powder, when it's in that finely divided state, it's not just rusting, it's burning very quickly. It's reacting very quickly, it's actually burning. Most other things, like nonmetals, will burn in air. That is, they'll make a lot of heat and a lot of light, and that is a consequence of their reaction with oxygen. So from now on, I need you to expect when you see something burning in air, it is almost always that thing reacting with oxygen in the air to make heat and light. That includes candles, matchsticks, gasoline, anything in our lives that burns. Nitrogen, that was oxygen. Nitrogen, on the other hand, our main component, is very inert and does not like to react with things. We breathe in into our lungs, each breath, more nitrogen than oxygen. And nitrogen does get into our blood, and it does go all over our body, and nitrogen comes right back out because it finds nothing to react with. The interesting thing about nitrogen is that it's a source for very important nitrogen compounds. Let's look briefly at these. In the biological world, plants and animals need nitrogen in their diet. In the sort of in nature, what you will find are microorganisms in the soil, sometimes in the plants themselves, like the roots of soybeans, that will take the nitrogen from the air and make it into compounds. It's called nitrogen fixation, usually compounds with oxygen, and that is how nitrogen can supply nitrogen compounds for biology. And if on an enormous scale you need to grow a lot of things like we do with modern agriculture. We need a lot of nitrogen fixation. Nitrogen in the air is combined in a chemical plant with hydrogen to make ammonia, and we hear the term anhydrous ammonia. And the anhydrous ammonia is put in large white sausage-shaped tanks and carted out onto the fields because that's the only way to get nitrogen from the air in large enough amounts into the soil so we can grow all the crops we need for our food and for our fuel. Moving along, we can go over here. We've got hydrogen up there. Please be aware hydrogen is not natural. We do not find it in the air significantly anyway. However, there is an awful lot of hydrogen in our life. Water has more hydrogen atoms in it than oxygen atoms. All our hydrocarbons, things that are oil-based and fuel-based, like from gasoline and things like that, loaded with hydrogen. So hydrogen we see because it can be taken out of those compounds so much, and it gets used a great deal, at least in the laboratory. What does hydrogen do? Well, hydrogen can react in certain ways. One of the more important things that it can do is it's flammable. It can burn and give off heat and light, just like a match or a candle or any other fuel. In fact, if economical ways are devised to get large enough amounts of hydrogen, on the order of the amount that we would get for comparable to the amount of oil that we get, hydrogen could be used as a fuel source in order to replace some of the fuels we have, the oil-based fuels. So that's gases. Let's look at solids. The gray regions are solids. They're solid nonmetals. They're solid metals. The interesting thing about metals is that they are all solid except one, and I'll get back to that in a minute. So when you run across a metal, at least at room temperature, here we go, you expect it to be solid like the metal blade of this scissors. While we're on metals, I'd like to look at a particular set of metals as well. The metals in the first column of the periodic table are referred to as alkali metals. Whoops. I don't think I can get it up here. We'll see. There it stayed. Alkali metals. I don't know if you can read that, but you need to know that that first column is alkali metals. And the reason we group those together is they have very interesting properties. I've got an example of it here, I think. I've got some water and something on top here. And I've got the alkali metal potassium. And what I'm going to do, I do believe I need here, this should do it. Something to cut the potassium. And if I take out a piece of potassium and cut off a little small piece of it, watch carefully, it'll happen quickly. I put it into some water and stood back, and what the potassium did is it reacted with the water. It reacted violently and it had a lot of heat. We expect that of alkali metals. They are very reactive, and we have to be very careful with them. They are an interesting, they have the interesting property we found with halogens as well. Once the alkali metals react with something, and be careful with these, they react violently with almost anything, the product that gets made, the compound that gets made when they react with something, is always very stable. So for example, potassium could react with chlorine and make potassium chloride, which would be a very stable compound. But potassium itself is very reactive. We expect that to be true of all these in the first column. I want you to know the name is alkali metals. Liquids at room temperature. There's one, halogen, bromine. I'm not going to dwell on that. We don't see that a great deal. But I would like to point out mercury. If I can find it. If I put it up close to you, maybe you can see a little bead of metal floating around in there. Okay, that's mercury. It runs around as a nice little liquid. Okay, but it has metal properties. It conducts electricity, it's shiny, certainly as a liquid it's malleable, and it has all the properties we associate with different metals.